So yeah, and it is wonderful to be here in Singapore. I have been meaning to visit the CQT. I don't know why I didn't make it here before, given that there's so many of my friends are here now, and it's just a convenient 20-hour flight away. But here I am. It's great to be here. So all right. So I want to tell you about some new work. So it's not even fully written up yet. But I've gotten I'm very interested in sort of some striking connections that were made, really just within the last 3 years, between quantum computing theory, which is where I've spent most of my time, and where many of you have, and things like the black hole information problem and the DSCF correspondence, which I am not expert in at all, but some of my friends are. So I've been working with them. Okay. All right, so my starting point, I would like to have bridges between physics and computer science, and for the last 20 years at least, a very big and obvious bridge has been quantum computing. Okay, and quantum computing has been such a striking connection between these fields that it is tempting for a computer scientist like me to think that everything that I might need to know about physics is contained in the definition of the complexity class BQP, right? I just need to know what a quantum computer is and what it does, and I can think of the universe itself as just a giant quantum computation. It's a huge collection of qubits, evolving by some unitary transformation, and and then I can just black box everything else about physics. It's just a bunch of encoding details. Okay, well whenever you're tempted to think like that, you're probably sweeping something important under the rug, and but I think understanding quantum information is this wonderful way to sort of get your feet wet in physics, and then what I've been doing in the last 6 years or so is sort of trying to go a tiny bit toward the deeper end of the pool, and so some of you might have seen the work we did on boson sampling, which is about quantum where we had to learn a little bit more about physics to do this. We had to learn what a boson and a fermion was, and we came up with this sort of model for a rudimentary type of quantum computer that would only involve non-interacting bosons, and this is now kind of a cool, experimental area, or people trying to implement this. Some of you may have seen that just this week a paper was published in Science doing this boson sampling protocol with 6 photons. The previous record having been 4. Okay, now if you could scale this up to about 30 photons, at that point you're doing something we think faster than any classical simulation of it. But with 6 photons, it's still pretty easy. But now, it's another type of connection that sort of, that I think goes beyond just, where you have to know a little bit more physics than just that contained in quantum information, is this connection that's, a bunch of people, Lenny Susskind, Patrick Hayden, and others have been exploring within the last few years. Between black holes and ADS-CFT and the and quantum information and complexity theory. Okay, so I'm going to tell you about that. I'm going to tell you about sort of my point of view on it, which concentrates on just the very, very interesting theoretical questions about quantum complexity theory, that are raised, that I think are interesting questions, even just apart from the black hole connection. Okay, and what some of the progress that we've been able to make on these questions. And more. Okay, whatever. Okay, so so it may seem outlandish that there would be a connection between black holes and complexity. So it's like I think one of the most exciting things for me within the last really in my whole career was to see this paper in 2013 by Daniel Harlow and Patrick Hayden. Which was about the firewall paradox, which is a sort of modern reincarnation of the black hole information paradox, posed by Stephen Hawking in the 1970s, and and they sort of mounted a very detailed argument that actually, quantum computing theory was going to be very relevant to understanding this puzzle, and I was sort of initially very skeptical of this, but I found the more I sort of wrestled with their argument, the more I liked it. So. But in order to sort of explain, what problem they were trying to address and so forth, I'll need to review 40 years of black hole history. I'm going to try to do that in one slide. Okay, so actually this story sort of starts with Jacob Bekenstein, who sadly passed away just a few days ago. But he was a graduate student of Wheeler's in Princeton, and and he started talking about black holes, like any other physical object, ought to satisfy the second law of thermodynamics, which means if you drop something into it, then there ought to you ought not to be able to decrease the universe's entropy in that way, at the very least. Okay, so the entropy ought to go somewhere. Where does it go, right? And if two black holes merge, that again ought to sort of increase entropy. And, you notice that if you just sort of assume that the surface area of a black hole's event horizon acted like an entropy, then that sort of made all the numbers work out. And then people said, well, this is crazy. That doesn't make sense because a black hole is just completely black, right? It's characterized by its mass and charge and angular momentum. So there's no room for any entropy there. Okay, so situation changed when Hawking did this calculation in quantum field theory in curved space-time that said, well, actually, what a faraway observer would see is, they would see something that looks a lot like radiation coming out, originating from, around the event horizon and coming out very, very, very slowly. So they would very slowly see the black hole, shrink as radiation comes out of it for a black hole the size of the mass of the sun. It would take about 10 to the 69, 10 to the 70th years or something for the black hole to evaporate. But you can make a very firm prediction that that's what's going to happen. Even though no one has ever gotten close enough to a black hole or waited for nearly long enough to see this process, quantum field theory is considered so well understood that essentially that almost everyone agrees about this prediction. Okay. They don't agree about the other stuff, that we'll come to. Okay, but now it was sort of almost immediately realized that that there was a problem with this. Okay, so yes, black holes have a temperature, they have an entropy, they eventually dissipate away. But Hawking's calculation, the same one that told you that this radiation was there at all, also predicted that the radiation would be thermal. Okay, it would be completely uncorrelated with whatever information had fallen into the black hole. Okay, and if that's really true, then that's a problem for our conventional understanding of quantum mechanics, because this would mean that pure states would be evolving into mixed states. Okay, it would mean that if you're a faraway observer, you cannot think of throwing something into the black hole and then waiting for the radiation to come out as just another example of a unitary scattering process, right? You would need to think of the information as irretrievably lost from the universe. Okay, and in some sense, reversibility has been one of the pillars of physics, since long before quantum mechanics, even since Galileo and Newton, right? So that's a pretty big thing to give up on. Okay, and so then people said, well, what we would really like is an account where if we drop some information into a black hole, then sure, it will get all scrambled up and become unrecognizable. Just like if you burned a book, it's going to be hard to recover it. Okay, but in the case of the burned book, we know that the information is there somehow in the smoke and ash. Okay, we know that because of the reversibility of the laws of physics, right? We know that in principle, an infinite intelligence that knew the complete state of the smoke and ash would be able to run the evolution equations backward and recover the words in the book. Okay, so we would like to think of a black hole as just a really souped up kind of fire or something. Okay, and so we can imagine that, okay, fine, quantum field theory, everyone knows, is just an approximate theory anyway. It is to be superseded eventually by a quantum theory of gravity, and so maybe that will be totally unitary and will explain how the information gets out. Okay, but then people noticed another problem, which is, if you standing outside of a black hole, you can, eventually see. Let's make it a qubit now. If you can see a qubit that you threw in come out eventually, well, okay, then fine. Then you think the qubit came out, but an observer who jumped into the black hole should also see that same qubit inside the black hole, because once it gets in, that observer should never see it come out, right? So then you would have two copies of the same qubit, but that would appear to violate the no cloning theorem. Okay, so people argued about that for a while in the 1980s, but then eventually they decided, okay, fine, well, as long as the same observer can't see both copies of the qubit, it's probably okay, right? And they did some calculations that I'm not making this, I'm not making up what they said. Okay, so they did some calculations that said, look, even if you stayed outside the black hole and you waited for one copy of the qubit to be reconstructible from the Hawking radiation, and then you immediately jumped into the black hole, motivated by your love of science to go look for the other copy. Well, by that time, the other copy would have long before hit the singularity. Okay, so it all seemed kind of okay for a while. Okay, but then you could say, well, look, if we're even talking about two copies of the same state, regardless of whether you can see both of them or not, just what is the Hilbert space here, right? What are we talking about? What is the space of states? Okay, so there's actually, an extremely radical proposal from the 1990s, and this got, I think very, very widely accepted without people just fully understanding just how radical it was. Okay, and that at least until this firewall problem came out. Okay, but the proposal that people converged around was called black hole complementarity, and what it essentially says is that jumping into the black hole is just this very, very convoluted way of sort of measuring the same degrees of freedom that are also present on and outside the event horizon. Okay, so in other words, there is not a separate part of Hilbert space that describes what's inside the black hole. That's all you do when you jump in the black hole is you measure stuff that's already outside the black hole but in a different basis. Okay, so it's okay for there to be two copies of a state, one inside and one outside, because they're not actually two copies. They're just the same state being measured in a different, being viewed in a different basis. Okay, and they had various arguments for why, strange as that sounds, that might be a reasonable thing to believe. And it never, I sort of knew about this. It never made a lot of sense to me. I never really understood it. And then what happened in 2012 was that, all the experts sort of decided that they didn't understand it either. and this was this firewall paradox. So let me explain this. Okay, this is Amhiri, Maroff, Polchinski, and Sully proposed sort of a very concrete thought experiment that, if you took all of the sort of, sort of accepted ideas about black holes and put them together, seem to lead to an absurdity. Okay, so you have to reject at least one of them. Okay, and what's nice about this is that they actually described an experiment. Okay, and so almost everyone wanted to sort of reject this paradox, I think, as sort of unimportant, as trivial. Of course, they didn't agree about why. But I think that anything that you're going to count as a resolution to this sort of has to say, what would you actually experience if you did this experiment, right? You have to give some answer to that question. Okay, so let me describe to you what the experiment is. Okay, so all right, so the experiment sort of is going to involve three regions, if you like. H is the interior of a black hole. Okay, and this we're going to call an old black hole, which means one that has already evaporated at least half of its qubits as Hawking radiation. Okay, so you've got to wait 10 to the 70th years or so for an astrophysical mass black hole to become old. Okay, but that's fine. We'll assume we have a really long grant or something. Okay, maybe here at CQT you guys have such grants. All right, so. All right, and now R is the Hawking radiation that's come out of the of the black hole, and has escaped to be far away, and B is going to be some Hawking radiation that is just now coming out of the black hole. Okay, so and for convenience, I'll often think of B as just a single qubit. Okay, that we want to focus on. Okay, now we consider an observer, Alice. Okay, and what you can show is that if Alice just staying outside of the black hole, makes a measurement on R and B, she can find that they are not in a completely thermal state. That they are, that in fact R and B are nearly maximally entangled with each other. Okay, now why is that? Okay, the reason is actually a very, very simple quantum information theory reason. It has nothing to do with the specifics of black holes. Okay, so it's, in other words, it's a reason that people in this room can understand. Okay, and what it is, okay, remember we assume that the black hole has more than halfway evaporated, right? Which means, if you think of this as just a system of n qubits, more than n over 2 of the qubits are now in R and B. Okay, they've come out. Okay, and now, if you consider any pure state. So all right, so we'll assume that we knew the complete state of the infalling matter that went to make the the black hole. That's fair game in a thought experiment. experiment like this, right? So, so the whole system started out in a known pure state. It collapsed, and now we look at more than n over 2 of the qubits of that pure state. Okay, those qubits cannot be in the maximally mixed state, right? Because there just aren't enough qubits in the H part to trace them out. Okay, so, which here corresponds to saying that these are not completely thermal. Okay, but moreover, if you look at, you take some n qubit state, say you make it reasonably scrambled up, and, and whatever are the dynamics, inside the black hole that are going to scramble, that are going to produce this Hawking radiation, it's reasonable to assume that they're going to scramble everything up a whole lot. Okay, make some very, very messy entangled state. Okay, so you take, let's say, a Har-random n qubit state. Doesn't have to be Har-random, just has to be, sufficiently scrambled in some sense. Okay, and you look at more than n over 2 qubits of it. Okay, and then you look at some, additional qubit. Okay, then you can prove for yourself that qubit will almost certainly be maximally entangled with the more than n over 2 qubits. Okay, it's just because of a dimension counting argument. That's all it is. Okay, so we say, there is, for this sort of information theoretic reason, there should be some unitary transformation that Alice can perform on the R and the B system that would show her that at least one, by acting unitarily, only on R, she should be able to distill at least one E-bit of entanglement between R and B. Okay, okay, but now the second part of the argument, this is sort of something you have to sort of, I guess take on faith about quantum field theory. Okay, quantum field theory says that the vacuum state is actually very, very highly entangled. Okay, if you want to have a smooth vacuum in quantum field theory, there has to be lots and lots of at least short range entanglement between these vacuum modes. In particular, there's like particle-antiparticle pairs that are constantly forming and annihilating, or that's one way to talk about it. Okay, and and these pairs are entangled. Okay, and in particular, if Alice wants to sail past the event horizon and see a smooth space-time, then these photons that are just coming out of the event horizon need to be maximally entangled with partner photons that are just inside the event horizon. Okay, which means that this B qubit, which she found to be maximally entangled with R, also needs to be maximally entangled with a qubit that's inside B. Okay, but now you can see the problem. Well, there is this thing called the monogamy of entanglement. Okay, the same qubit cannot be maximally entangled with two other qubits. That doesn't, and furthermore, this is not just like some conceptual issue. This is, Alice can, should actually be able to see this entanglement and this one, right? Which means that, she is, we now have an actual observer who is seeing a sequence of things that is just not consistent with any underlying quantum state. Okay, and so the amps suggested a sort of a very radical way out, which is, well, maybe, when Alice hits the event horizon, so already there, long before she gets to the singularity, she's just going to encounter an end of space-time. Okay, that's what's called the firewall. All right. But really, it's a question of, which assumption do you reject here? Okay. So I should say that, there's a whole bunch of resolutions that have been proposed. One of the simplest, you can just deny the assumption that the information comes out. You give up on the reversibility of the laws of physics, but you've got no firewall problem then. Okay. Or you could just accept that these firewalls form. You could do you could make a sort of radical positivist move, and you could say, well, look, the problem only occurs when Alice jumps into the event horizon to see what's on the other side. Okay, but once she's behind the event horizon, she can't publish a paper about it anyway. Okay, or she can only publish a paper, to be read by other people who also jump jumped in. Okay, so maybe we could just say what happens in a black hole stays in a black hole. It's not part of our empirical world. Okay, so you could do that, or you could just say, the firewall forums, deal with it, or I think that the type of answer that a lot of people have gravitated to, so to speak, is to say something like, well, yes, if Alice did this bizarre measurement on the Hawking radiation, she could cause a firewall to form, okay? And that shouldn't be surprising if you believed in black hole complementarity, right? Because if you actually believed that, that what is inside the black hole is just this scrambled re-encoding of the same qubits that are already outside the black hole, well then of course there must be some unitary that you could apply to the qubits that are outside the, the black hole that is going to completely mess up what you see inside the black hole, because they're the same qubits. Okay, so from that point of view, the problem is not just that Alice, it's not surprising that Alice can do something that would create a firewall, but what you want to reassure yourself about is that this is not going to happen in ordinary circumstances. Okay, and why would someone worry about that? Well, basically because physicists thought that they understood general relativity and quantum field theory sort of very, very well, and those theories led to sort of a firm prediction that the event horizon, as you're sailing past it, should not look like a special place. Okay, it should just look like pretty much anything else. Okay, and and they would like to sort of be able to uphold that understanding. Like they knew that it would break down if you could, do if you went up to Planck scale energies or something. But but that sort of picture should be upheld under ordinary conditions. All right, so the so now we come to a question about what do we mean by ordinary conditions, right? Or like we want to say that it would be really hard, it would at least be really hard for Alice to make this firewall. But what do we mean by really hard? Okay, this is where Harlow and Hayden argued that complexity theory enters the picture. So what they did is they gave, I think, a striking argument that just Alice's first task, which is decoding the showing that there is entanglement between R and B, would already require an exponentially long quantum computation. Okay, which would mean that sort of long before Alice had made a dent in solving this problem, the black hole would have long ago evaporated anyway. Okay, so just to sort of put some numbers on it, for an astrophysical black hole, they're saying her decoding task could take something like 2 to the 10 to the 70th years. Okay, whereas remember the black hole is going to be gone in a mere 10 to the 70th years. Okay. So maybe there's no problem. So a lot of people were very uneasy about that, and they said, well, look, surely you must not be saying that it's okay for there to be an inconsistency in the laws of physics, as long as it takes exponential time to discover it. Okay, but I think that that's not what they're saying. Okay, presumably in the true quantum theory of gravity, everything is consistent. There's no contradiction. Okay, but low energy quantum field theory we knew from the beginning was just an approximate theory. Like we knew that it has to break down when you go up to Planck scale energies, for example. Okay, and what they're suggesting is that even if you don't go to Planck scale energies, it could also break down if you were able to do an exponentially hard computation. Okay, so it is, I think, a novel use of complexity theory or a novel proposed use of complexity theory in fundamental physics, but maybe not quite as radical as one might have thought. Yeah. Okay. So there are some obvious caveats of any complexity argument that probably most of you know well. Okay, the first is that of course complexity theory, as we usually do it, is only able to talk about asymptotics, right? So the standard joke is that for a complexity theorist, chess is a completely trivial game. It's solvable in O of 1 time. Okay, just enumerate all the board positions. There's 10 to the 160 or whatever, but that just goes inside the big O. Okay, so we can only talk about sort of the rate of growth of hardness as a problem gets larger. Okay, but then you might worry. Well, but then what? Surely even if the problem took time that's exponential in the number of qubits of a black hole, then the argument wouldn't work for a microscopic black hole, for example, right? For a microscopic black hole, you would have an easy problem. Okay, but that actually turns out not to be an issue. And the reason is that for microscopic black holes, if they exist at all, no one ever expected low energy field theory to be a good description anyway. Okay, so people are not worried about that. They're sort of they're only worried about this for very large black holes, the ones where they expected field theory to approximately work. Okay, now. Of course, in complexity theory, you have to get used to the fact that, well, we can't even prove, P is not equal to NP in our current state of knowledge. Okay, I like to say that, if we were physicists, we would have just defined P not equal to NP to be a law of nature and been done with it. Okay, but, because we're mathematicians, we call it a conjecture. Okay, and but in fact, in complexity theory, if you can sort of say that your problem is hard, merely assuming that P is not equal to NP, then that is like that's like the gold standard. Okay, that is an incredibly strong argument for the hardness of your problem. Okay, most of we're very very often we cannot even do that. Right, we strive to do that. Okay, but often we need to make stronger assumptions than just P is not equal to NP, like assume that a particular cryptographic code is secure or something like that. Okay, so but in this talk we will be concerned with the issue of what is the weakest assumption that we can make to get our problem to be hard. Okay, and then thirdly, complexity theory most of the time is worst case, which means that we would be able to argue that there is some instance of our problem that's hard, but then you might worry that, well, maybe because of some yet unknown laws of quantum gravity, maybe even if the generic case of some problem is hard, maybe for actual black holes that would form in our world, maybe you wouldn't have to deal with the generic case of the problem, right? Maybe there would be some symmetry or something that made it easier. Okay, well, in fact, once you see the sort of the details of the situation, I think intuitively the sort of realistic case of the problem should, if anything, be harder than the special cases that one is able to give a formal reduction for. Okay, but I don't know how to formalize that, but I'll show you. Okay, so all right, so the first step that Harlow and Hayden do is to sort of model, whatever is the state of the black hole as a finite collection of qubits. Okay, that's justified by the Bekenstein bound, or the holographic bound, that upper bound the number of qubits in any region by basically at most the surface area of the region in Planck units. Okay, and whatever are the dynamics going on in the black hole, it's assumed to be some quantum circuit. Okay, so a bunch of local unitary transformations acting on a few qubits at a time, and we'll assume that it's known, right? We'll assume that we know the laws of physics. Okay, so then we can define like the Harlow-Hayden decoding problem as follows. You're given a description of a quantum circuit C, which takes some simple initial state, like the all-zero state, and prepares from it a pure state psi of these three regions, R, B, and H. Okay, and now you're promised that this psi has the property that by acting only on R, so only on the old Hawking radiation part, it is possible to distill an EPR pair between R and B. Okay, well, we'll assume that B is just one qubit. Okay, but it is possible to put B into, an EPR pair with, let's say, the last qubit of R. Okay, and now your task is to distill such an EPR pair, okay, by applying a unitary transformation U sub R to the qubits in R. Okay, so you want to make manifest that R and B are entangled. Okay, so the first thought when you see this problem is, well, shouldn't the decoding task just be trivial? Because if we know a complete description of the quantum circuit that that gave rise to this black hole, well then just run the circuit backwards, just invert it. Okay, there's a problem with it. You can probably see it yourself if you think about it. To apply the inverting circuit would require access to all the qubits, including the qubits that are still in the black hole. Okay, or on the event horizon, depending on your point of view, I guess. But so that would require waiting until the black hole had evaporated, at which point there's no more firewall problem. Okay, so. We saw, okay, so what you want to do is apply a unitary only to the R part, that has this effect. Now, I gave you this information theoretic argument earlier that such a unitary must exist, right? But the argument I gave was just an abstract dimension counting argument. It did not suggest any efficient procedure to actually apply that unitary. Okay, and that already might suggest to you that, well, maybe no efficient procedure exists, right? Maybe this is just, even though this unitary U sub R exists, that it would be exponentially hard to apply. All right, so that's already plausible, but Harlow and Hayden wanted more than a plausibility argument. Okay, and what we usually do in complexity theory is we try to give a reduction. Okay, so, we can't prove that the problem is hard, but we at least try to pass the blame to someone else and say, well, if the problem is easy, then all these these 100 other things that you thought were hard are also easy. Okay, so to state their hardness result, so we can use a problem called set equality. Okay, so this is, you're given two injective functions f and g. Let's say each one mapping n bits to some polynomial number of bits. And we can think of these, if we like, as just, efficiently computable functions for which, you're given a circuit to compute them. Or if you prefer, you can also just think of them as black boxes, okay, that can be queried in quantum superposition. Okay, either perspective is okay. And but now you're promised that f and g, let's say, have either equal ranges or disjoint ranges. Okay, and your challenge is to decide which. Okay, that's the set equality problem. Now, in the case where f and g are just abstract black boxes, we actually understand now the complexity of this problem. Okay, so one of the main things that I did in my PhD thesis in 2004 or so is that I proved sort of the first non-constant lower bound for this on the number of queries that to f and g that a quantum computer needs to solve this kind of problem. Okay, so you may have heard of that as the collision lower bound, which is a very related problem where you're given a function that you're promised is either 1-to-1 or 2-to-1, and you need to decide which. So set equality is just a slightly more structured version of that. And so in 2002, I proved that any quantum algorithm to solve set equality in the black black box case, has to make at least about 2 to the n over 7 queries to f and g. Okay, so it could get at most a polynomial improvement over the just sort of obvious brute force strategy of just doing the birthday attack, sort of, and looking for collisions. So the best algorithm that we've known is due to Broussard, Hoyer, and Tapp. It takes 2 to the n over 3 queries with a quantum computer, compared to the classical birthday attack, which would be 2 to the n over 2. And you get that 2 to the n over 3 by sort of combining the birthday attack with Grover's algorithm in a clever way. Okay, so now we conjecture that 2 to the n over 3 was actually optimal. That remained open, but that was solved about a year ago by Mark Jandry. Okay, so we now know that 2 to the n over 3 is the truth. All right, but even if you don't like this black box model, you want to assume that f and g are described to you explicitly, still you can say, well, look, if you had an efficient quantum algorithm for set equality, that would, for example, give you an efficient quantum algorithm for the graph isomorphism problem, which would be a very, very striking discovery, right? And why is that? Well, just suppose you have 2 graphs. You want to know whether they're isomorphic or not. Okay, so now let f, consist of let all the values of f consist of all the possible permutations of your first graph. Okay, and let the values of g consist of all the possible permutations of your second graph. Right. So you could say g of f of sigma is sigma of permutation sigma applied to the first graph, and likewise for g of sigma. Okay, so now we've defined 2 functions such that if the graphs are not isomorphic, then these functions have disjoint ranges. If the graphs are isomorphic, then they have the same range. Okay, so this is if there's a quantum algorithm to do this sort of thing, then there's a quantum algorithm for a lot of other things that would be a very, very big deal. Okay, so now what Harlow and Hayden proved is that if there is a polynomial time quantum algorithm for this generic HH decoding problem, then there is also a polynomial time quantum algorithm for set equality. Okay, let's say when f and g are given to you explicitly. Okay, and once you've set this up, the proof of it is very, very simple. There's some construction. So you take the f and g for which you want to solve set equality, and you imagine having a state like this, where inside the black hole is the evaluations of f and g. And in the Hawking radiation is a superposition over all the possible inputs x, and then we sort of do this thing over here, and so actually, like, I've given away to you for free which qubit of R is supposed to be entangled with B, namely this last one. Okay, and you can already see that they're classically correlated, right? But in order to sort of reveal that they were entangled, you can sort of see that, well, what would you have to do? Well, if f and g have disjoint ranges, then actually they're not entangled. Okay, then this this h register in that case just sort of decoheres the entanglement that would have been there. Okay, if f and g have equal ranges, then they are entangled. Okay, but in order to see that they were entangled, you would sort of have to you would sort of have to solve the set equality problem, right? So, like, if you had suppose you had a procedure that worked to show that the things were entangled when f and g had equal ranges. Okay, then you could run that procedure and then just see whether it succeeded in making the entanglement or not. And if it did, then you would know that f and g had equal ranges. And if it didn't succeed, you would know that they had disjoint ranges. Okay, so in that way, you would solve set equality. All right, yeah, good. Okay, so a couple years ago, I found a strengthening of Harlow and Hayden's argument, where now it no longer relies on my PhD thesis. Okay, now actually I can base the hardness argument on a much more generic assumption, which is simply that there exists a one-way function which is hard to invert using a quantum computer. Okay, and that's something that I think that is really just assuming very little more than just that NP-complete problems are hard to solve with a quantum computer, right? So if you wanted like a public So as most of you know, quantum computer could break, almost all of the public key cryptography that we use today on the internet, right? There are a few theoretical public key crypto systems, like lattice-based crypto systems, that we don't know how to break, even with a quantum computer. Okay, but if you only wanted a private key crypto system, then you could just do sort of, or let's say, or more or less equivalently, if you wanted a one-way function, which was hard to invert with a quantum computer, and it didn't have to be a trapdoor one-way function. Okay, then you could just sort of invent any kind of scrambling transformation of your input, right? And if it's just sufficiently unstructured and scrambling, then it'll sort of be a plausible conjecture. The best way to invert it will be to do Grover's algorithm or something like that. Okay, and so I think it's very, plausible that there are quantumly secure one-way functions. And assuming that there are, we can argue that the Harlow-Hayden decoding problem is hard. In fact, even that it's hard to see classical correlation between R and B, let alone entanglement. Okay, and so we can use a different construction. This construction uses the notion of a hardcore predicate. Okay, so there's a famous theorem in theoretical computer science called the Goldreich-Levin theorem, which says that every one-way function has a hardcore predicate, which is like some bit about x, which cannot be predicted better than chance if all I told you is f of x. F being your one-way function. Okay, and an example of a hardcore predicate is like, well, here I've actually modified the function to make it have a hardcore predicate. I put in an extra string s, and then I just look at the inner product mod 2 between x and this other string. Okay, that's a hardcore predicate. Although, I love using this because, Goldreich and Levin are, neither of them believes in quantum computing at all. But, their theorem is still a perfectly good theorem and can be used not only for quantum computing but for quantum black holes. Okay, so then we'll have some additional bit a, and we will sort of exclusive OR this hardcore bit with a. Okay, and we'll set it up in such a way that in order to sort of transform R in a way that would make these that would show you that these two bits are correlated, you basically have to learn the hardcore bit of x, given only f of x and s. But if you can do that, then Goldreich-Levin says that you could invert f. Okay, that's the basic idea. So this leads to sort of a very funny picture where, computational intractability is this armor protecting the geometry of space-time inside the black hole. Okay, you can, completely mess up the geometry of space-time, at least if you jump into a black hole, but only by, inverting a one-way function or something like that. Okay, so I want to tell you about, so in the last couple of years there's been a lot of sort of interest in connections between, quantum gravity and complexity, and one of the proponents of this has been Lenny Susskind. So we have some work in progress where I've just sort of I just sort of offer my services to anyone as a complexity consultant, but he sort of made use of that, and so this this work involves the DSCF Correspondence, which is this proposed duality between sort of theories involving gravity, in d dimensions in a it's called an ADS space, an anti-de Sitter space, and a conformal field theory, which is a more or less, ordinary quantum field theory without gravity in d-1 dimensions. Okay, which if you like lives on the boundary of the ADS space. Okay, so it's a proposal that theory describing this gravity in a bulk region, and black holes forming and evaporating and stuff like that is in some way dual to a theory that lives only on the boundary of that region. Okay, this should be familiar from black hole complementarity, right? It's related. Okay, but there's an extremely like the two, well, what does that mean? It means that these two theories somehow have the same Hilbert space. They're just different ways of looking at the state. Okay, and there's some mapping between states of a one-to-one mapping between states in the one and states in the other, but this mapping is very, very non-local. Okay. And I should say that no one has proved this correspondence. Okay, by the string theorist standards, it's considered extremely well established. Okay, because whenever they can calculate one number on the ADS side and the same number on the CFT side, they get the same number, and they tried it a whole bunch of times, and so but one thing that was found was that if you create a state on the in the ADS side that just involves, let's say, a wormhole connecting two different regions of space, and let's say that this is so there's something called the thermofield double state that involves this wormhole connecting two regions, and a wormhole will just tend to get in GR will just tend to get longer and longer and longer until it pinches off. Okay, and whether that's in a finite or an infinite amount of time depends on which coordinates you're using. But then you can look at what is dual to that in the CFT, and what it is it's just a collection of qubits which are maximally entangled, with one half of the qubits being on one of the spaces connected by the wormhole, the other half being on the other half, and then this sort of entanglement just gets more and more scrambled up over time. So you can imagine just a unitary that gets applied more and more to one side of it, or if you prefer, a unitary applied to one side and its inverse applied to the other side. So it's the same thing. Okay, so now Susskind posed the following question. He asked, on the ADS side, something is clearly happening. The wormhole is getting longer and longer. Okay, what quantity can we point to, on the CFT side, which is dual to wormhole length? Okay, and so I should say there was a problem, right? Which is that if you look at pretty much any ordinary physical observable on the CFT side, like you look at what are called k-point correlation functions, okay, they just very, very quickly saturate. Okay, why is that? Because you just have some scrambling unitary transformation acting on a bunch of qubits, and that unitary will just tend to very, very quickly make the state look locally like the maximally mixed state, right? So then it just, it's like you pour some milk into coffee, right? It just something happens initially, it gets all stirred up, but then once it's stirred up, nothing much more happens. Okay, so but then the problem is over on the ADS side, the wormhole just keeps getting longer and longer. So something more must be happening, right? And indeed we know that something more is happening on the CFT side, which is, you still have a pure state, right? Your quantum state is still, rotating somehow through Hilbert space, but what sort of physical quantity can you point to that's getting larger and larger besides just the tautological one of, the amount of time that this quantum state has evolved for? Okay, so what Susskind proposed is that, well, what you really want to be looking at is the quantum circuit complexity of the state. Okay, and that simply means, the minimum number of quantum gates that you would need to prepare the state, if you started from a very simple state, like, the all-zero state. Okay, that's what quantum circuit complexity means. And, that's an intrinsic property of a state, right? But, if I just keep... So if I apply sort of T quantum gates, let's say, to the all-zero state, then it's clear that I'll produce a state whose quantum circuit complexity is at most T, right? So this quantum circuit complexity can at most grow linearly with the amount of time that I've evolved the system for. The other thing that we know is, now you might just hand wave and say, well, let's say that it's more or less linear, right? That there's no way to speed it up. Okay, but now quantum circuit complexity also has to hit a maximum at 2 to the n. Okay, because if you take any pure state of n qubits, you could always prepare it by a quantum state with at most about 2 to the n gates by just going basis state by basis state or something. Okay, so it's gotta hit a maximum here. By the way, there will be recurrences. This will dip down again after something like 2 to the n time, which is not even in this room. Okay, so this is how you might expect the circuit complexity of psi t to behave as a function of t. And now there were independent reasons from quantum gravity to expect the wormhole length to behave like this too. That it should keep getting longer and longer, but after an exponential time, it should stop. It ought to stop growing if you pass the quantum gravity. Okay. Now I think for the string theorists, that was as good as a proof that the two things must be the same. Okay, but you might want to do a little bit better. So the question that Lenny asked me was, can you actually prove that this circuit complexity of such a state will be increasing linearly as a function of time? That there's no shortcut to computing it. And so the first thing that I said was, well, look, we just, you got to get used to the fact that in complexity theory we don't prove things, like that, right? We don't, it's just too hard to prove such statements, and if we could do that we would have to prove circuit lower bounds. And he said, well, fine, but can you prove that follows from one of you people's reasonable assumptions, right? And I said, well, maybe. So all right, so that's so here's a theorem I can prove that suppose that our unitary is implementing, let's say, a computationally universal, reversible cellular automaton. Okay, and so in other words, all I need to assume something about the unitary, right? If it were the identity, then obviously it's not going to be making complex states. Okay, and so you might say, well, what we should be assuming is that U is chaotic or something, or has some, positive Lyapunov exponent or something like that. Okay, in fact, what turns out to be the crucial thing to assume is just that U is computationally universal. Okay, that it is possible to sort of take a Turing machine and encode it into U. Okay, that's the property I need, but that's a pretty plausible property for a unitary in the physical world to have, right?
Classical cellular automaton?
Yeah, all I need is a classical one for this. I mean, it could be a quantum one too, but all I'm going to need is a classical one will be perfectly fine. Okay. And and so then if you've got that, then after an exponential number of iterations, the circuit complexity of your state, will at least be more than polynomial in n, unless you get a very unlikely collapse of complexity classes. That PSPACE would be in PP/poly. If you don't know what that means, it's bad. Okay, so. Of course, Lenny wanted something stronger, which is that the C of t would actually be linear in t, right? Or that C of psi 2 to the n would be exponential in n. You can get those stronger conclusions if you'll make a stronger assumption, okay, that PSPACE, say, requires exponential sized circuits of a certain kind. Okay, so the proof of this, involves something that I showed in 2004, which was a characterization of quantum computing with post-selection. Okay, so there's a complexity class called post-BQP, which is all the things you can do in polynomial time with a quantum computer if you get to measure some qubit and then just condition on getting an outcome of 1, let's say. Okay, then that's a very powerful model of computation. I proved that it's exactly equivalent in power to PP, which is this probabilistic polynomial time class. Okay, so now what you do is you say, suppose by contradiction that your state, always had a polynomial circuit complexity. Okay, then you could give, what that means is you could give a description of the circuit, as advice to, you could give a description of the state, let's say, that should be the state, as advice to a post-BQP machine, and then the machine could just efficiently prepare a state like this. Okay, so the machine could prepare psi t, right, by the assumption that this had a small circuit complexity. Okay, and psi t, recall, should look like that. Okay, but now what you could do is you can just measure the first register and post-select on getting as an outcome the input x that you care about. Right, let's say x is some input that you have for which you want to know the solution to a p-space complete problem. So then all you do is you measure this first register and you post-select on getting x. If you got x, then what is going to be in the second register? Well, what's going to be there is ut of x. Okay, which is the evaluation, let's say, the running of the cellular automaton on the starting state x for an exponential number of steps. Okay, which can then encode the solution to a p-space complete problem. Okay, so then you get p-space in post-BQP with polynomial-sized advice. All right, so there are also results for approximate circuit complexity, and more. Some complexity assumption has to be made if you want a lower bound, but maybe you can do it with a weaker assumption than this one. I don't know. Okay, so there's lots of other, I think this whole area of the understanding what is the complexity of preparing a given state or of applying a given unitary transformation is something with a lot more richness in it, to explore. So it's had other applications, including to publicly verifiable quantum money that you could spend but that you wouldn't be able to copy, basically because of the no cloning theorem. But this is sort of a whole nother talk, and I'm sort of running out of time. So I had some more slides about just this issue of the complexity of preparing a state or applying a unitary transformation for other applications than quantum gravity. But I think that I'll skip this unless people want to ask about it. So we had some recent results classifying all the possible reversible gates, which also sort of came out of this goal of sort of understanding the complex, the ability to apply physical transformations to a given state, rather than just complexity. My student Luke Schaefer had what's called a physically universal cellular automaton, which is an automaton that can do any desired physical transformation in a given region. So any mapping from states to states by suitably initializing the complement of that region. Okay, so so this is an automaton that's more than just computationally universal, right? It's universal in this stronger physical sense that you can transform the state in any way that you want. Okay, so the summary is that I think we know something, but not enough, about which models of computation are universal in the computational sense. Which sort of decision problems or search problems can be efficiently solved by a quantum computer. But a major challenge is to understand which quantum states can be efficiently prepared, which unitaries can be efficiently applied, and which models of computation are physically universal in the sense that you can actually like do any physical experiment that you want, whether it's, you know, some given transformation of states of a cellular automaton, or setting up a firewall, or something like that. And, you know, the applications range from quantum money to quantum gravity. So, all right, so I'll stop there. Thanks.
Well, any questions?
Yeah.
Suppose you prepared an entangled black hole.
Yes.
Say,
Uh-huh.
and then the Hawking radiation comes out for some time.
Uh-huh.
Then wouldn't it be true that Alice already knows that the black hole is entangled with the system with which she entangled it in the beginning, and then the Hawking radiation comes out, it's already entangled. So the black hole is entangled with both the Hawking radiation and the system with which Alice prepared it to be entangled.
So, okay, so this firewall, you know, paradox, so I sort of just assumed, you know, like that we started the whole thing out in a pure state, right? And we just, you know, waited for it to collapse. Now, there was a paper by Jonathan Oppenheim and Bill Unruh that considered something that I think is very close to what you're talking about, right? Where they basically said, well, you know, you can, Alice can sort of, before she even prepares the black hole, she can prepare like two entangled registers, right? So then, you know, she already knows she's already able to, you know, decode the entanglement because of this, right? And basically in their version of the firewall paradox, Alice still has to invest exponential computation, okay? But the exponential computation that she has to invest, all of it is prior to the black hole forming, okay? So she does all of this stuff up front, you know, ahead of time, right? And then she forms the black hole, and then having done all this stuff, you know, which is a very, very special black hole now, right? When using all this stuff that she, you know, meticulously prepared, okay? But then using all that work that she did before, you know, they then argue that she could solve the Harlow-Hayden decoding problem in polynomial time, and then go see the firewall, okay? Now, you know, I think from the point of view that I've been exploring in this talk, you know, the answer to that will be, well, you know, if that's what you want to do, then sure, you can see a firewall. But, you know, you know, it's not going to happen for like a natural astrophysical black hole, you know, by doing any easy computation.
Sorry,
yeah.
Natural astrophysical black hole itself might be a very special state and not a highly entangled.
Yeah, but then it sort of. So the argument that you would make at this point is that, you know, if you look at sort of, you know, if you just imagine that whatever unitary transformation is happening in the Hall is just scrambling things up in a more or less generic way, right? Then okay, of course you're not going to get states that look like the, let me go back, you know, these like weird states that we use for the reduction, okay? But in some sense the states will be even worse from the point of view of Alice's decoding task, okay? Because you'll get like a collection of, you know, of let's say computational basis states over here, right? But then over here there'll just be some like psi sub x for each x, right? It won't even be a classical state, right? It'll just be some totally arbitrary quantum pure state depending on x, right? So like, why should that make things any easier, right? You know, if anything, it should make things harder, right? You know, now that's not a formal argument, but that's sort of the intuition.
Please, Joe.
Yeah.
So I just have a question about this idea. So
yeah.
being kind of in your talk, it's kind of taken for granted that you can describe the inside of the black hole by some set of qubits.
Yes.
Rather to the observer. You know, we use some outside observer.
Yep.
And you're in the coordinate system for the outside observer. But when you have this kind of removable singularity that the event horizon. Crossing that kind of interchanges the role of space and time, right? You pick up this line in front of things. Is it clear that you can still, I mean, that qubits have the same meaning, that the nature of correlations must obey monotony?
Well, okay, so I don't think any of this is entirely clear, okay, but I can tell you what the complementarity point of view would be, right? The point of view of complementarity basically says, as long as you are staying outside the event horizon, you're never going in it, you can describe, you know, all of your observations by just imagining that, you know, basically there is no interior, okay? You can just imagine that whatever whatever, information you're throwing onto the event horizon, it is, of course you'll never actually see it go in because of time dilation, right? You'll just see it, get slower and slower, and but it will just somehow just sort of get pancaked around, the event horizon, or what they call the stretched horizon, which is like one Planck length above the event horizon, right? And it'll just sort of hang out there for a while, and then these qubits will, very, very slowly sort of fizzle off as Hawking radiation, right? But the aspiration would be that you should be able to describe all of your observations in terms of just a unitary transformations happening to qubits, in that space, without ever making reference to anything inside the event horizon. Okay, you only have to think about what's inside the event horizon if you actually jump in, and then what you see is is again the same qubits, but you're sort of measuring them in a different basis. Okay. Yeah?
About this Susskind idea about the wormhole and versus the circuit complexity.
Yes.
One thing that seems a little weird about that to me is that I would expect that the length of a wormhole would be something that would be an expected value of some observable in the traditional sense.
Yep.
Whereas it seems like circuit complexity
is not.
In the States is really wildly.
Yes. That's an excellent point. It's something that I've actually pushed Lenny about a lot. Okay, and and what he points out is that the length of a wormhole is actually not clearly unobservable. Okay, and so and the reason is that this it's sort of pinched off, right? This wormhole is not a traversable wormhole, right? And so basically, what you get is that where is it? So if Alice jumps into this side and Bob jumps into that side, they may be able to communicate and compare notes, but they're never going to get the notes out. Okay, so to an observer at infinity, right, there is not clearly any observable that corresponds to the length of this wormhole. Which means that okay, it is not admittedly, it is not entirely clear what we're talking about, right? I mean, the length of the wormhole was something that would be well defined in classical GR, right? But now we're trying to give it some meaning in a quantum theory of gravity, which we don't yet know what it is, right? But but in some sense, the way that we give things meaning in ADS-CFT, the way that we give meaning to things in the bulk is to find what is dual to them in the CFT, right? And so now we're taking something that's not an observable on the ADS side, and we're sort of postulating that it's sort of dual to something that's also not an observable on the CFT side. So if you so Susskind has a series of papers where he gives arguments for why this identification is a good one. What they do is they do a whole bunch of different thought experiments where you can do something like send a shock wave into the wormhole that would stop its growth, or that would turn around its growth for a while, okay, or things like that. And then in each of these cases they calculate what happens to the circuit complexity, and they find that in every case they get a match, right? So this is what sort of convinced them, I think. It's by Susskind and Douglas Stanford, these papers that now I would tend to say this is one should be cautious in making an identification like this. For one thing, because there are different variants of quantum circuit complexity, right? There are we could put a bound on the number of ancilla qubits, or we could not, right? We could say that the unitary transformation is only allowed to act on one side of the EPR pair, right? Or we could say that it's allowed to act on both sides. Right, so there are different choices that we could make, and then, we would face the question, okay, which of these is the one that is dual to the wormhole length, right? So I would, tend to make a weaker claim, which is just, this was a useful diagnostic for what's going on, right? It is something that is sort of, observed to be correlated with, in many cases, with the wormhole length, okay? But, of course, correlation doesn't have to imply causation, right? There could be some third factor, which is responsible for both the wormhole getting longer and the circuit complexity going up. But, in any case, I think all of these questions are somehow above my pay grade, right? And, what I'm sure about is that if PSPACE is not in PP/poly, which I'm pretty damn sure it isn't, then the state is complex. Yeah.
Any other question? If not, then I guess it's time to thank Scott for this really inspiring.